Hi, I'm Kimo Johnson, co-founder and chief product officer at GelSight. I'm going to tell you a bit about the history of the technology, the company, and introduce you to some of our products. GelSight was introduced to the world in two academic papers, retrographic sensing for the measurement of surface texture and shape from CVPR 2009, and microgeometry capture using an elastomeric sensor from SIGGRAPH 2011. While these are the academic origins of the technology, the idea was conceived by Professor Ted Adelson as he watched his infant daughter interact with the world through touch. Human skin is soft and highly sensitive, yet the touch sensors we interact with on a daily basis are rigid, low resolution, and do not capture a signal comparable to human tactile sensing. The lack of commonly available tactile sensors with capabilities similar to human skin results in human hands being critical to many tasks, from handling delicate objects to assembling products and inspecting surfaces. The GelSight sensor provides a novel method for digitizing touch. The key idea is an elastomeric sensor with a thin layer of paint on the surface. When an object touches the sensor, the layer of paint closely conforms to the surface topography of the object. Using a camera, tactile interactions can be digitized at high resolution and combined with computer vision algorithms to produce 3D data and other high-level information. The first GelSight system was presented at SIGGRAPH Emerging Technologies and CVPR in 2009, where it won the Best Demo Award. This version used a single-color camera with red, green, and blue lights to capture 3D information in real time. This 3D measurement strategy is known as photometric stereo, and it provides estimates of local surface slope at every pixel in the image. Even in the first system, the sensitivity of the system was impressive, as it was able to measure the raised printing on a $20 bill. After the first paper, we improved the resolution of the system through changes to the elastomeric sensor, illumination design, and computer vision algorithms. With these improvements, we were able to demonstrate a method for measuring microgeometry that was independent of the optical properties of the material. This method was demonstrated on diverse materials such as leather, glass, fabric, and metal, and the measured microgeometry was used to create realistic renderings of the materials. This work generated interest outside our academic community, and in 2011 we founded the company to commercialize the technology. We started by selling benchtop measurement systems to research labs, and over the years, we made the system smaller and more capable. In 2018, we launched GelSight Mobile, a handheld 3D measurement system for inspecting surfaces at the micron scale. And this year, we have introduced GelSight Mobile Series 2, a smaller and more capable system that incorporates feedback from our customers. Our management team has diverse backgrounds, including executive experience in optics, photonics, aerospace, and technology commercialization, combined with strong scientific leadership. Our product family includes the GelSight Mobile 3D measurement system, a robotic finger to enable research on tactile sensing, and several types of gel. Our software libraries and applications allow our customers to use these systems for measurement tasks or integrate the sensors into their own products. The GelSight Mobile Series 2 is used for non-destructive inspection of components in industries including aerospace, automotive, and consumer goods. The system can be used as a handheld tool or integrated into a robotic inspection system. The software allows for fast measurement of dimensions with a touchscreen interface. Some common measurements are inspecting components for damage as part of new production or maintenance workflows. On this slide, we are showing some aerospace components measured by our customers, where quality inspectors are using our systems to make decisions on whether components should be repaired or replaced. In many cases, the ability to make the measurement on the factory floor can save hours, if not days, compared to conventional inspection processes in the industry. Our customers appreciate the versatility of the system. It's precise, fast, and repeatable across different operators. The measurement is digital and can be archived for traceability. And finally, due to the unique properties of the GelSight sensor, the system can be used on a wide variety of materials with the same ease of use. I'd like to give you a demo of the new GelSight Mobile Series 2. This is the Series 2. It's much smaller than our original probe, and it allows our customers to get into tighter locations that they couldn't originally access. A standard workflow would be when a customer finds a defect in a component, such as this fan blade. Press the device up against the edge of the blade, and with the press of a button, we can get a detailed 3D measurement of that defect. Using our touchscreen software, our customers can quickly analyze the defect they just measured. Here, I'm extracting a profile across this dent I'm leveling it, and I'm configuring the software to find the bottom to tell us how deep it is. The software tells me that it's about 120 microns. Within about a minute, I've measured the defect, I've created a report, and this could be sent to a quality management team who needs to decide if this can be repaired or replaced. Beyond dimensional measurements, we are also developing methods to replace quality control processes involving visual inspection. In this example, a customer is inspecting wood samples for automotive interiors. We have demonstrated that GelSight measurements combined with machine learning strategies is an effective substitute for human visual inspection, as the machine can classify the samples according to their perceived quality. We are also interested in exploring commercial applications of robotic tactile sensing. Funded by a Phase 2 SBIR grant from the National Science Foundation, we are developing smaller sensors that can be attached to robotic grippers. These sensors build upon academic work on GelSight and robotics that has demonstrated the ability to sense shape, pose, slip, hardness, and other tactile signals. Our goal is to make GelSight technology more widely available to robotics researchers. This is the new version of the GelSight robotic finger. It has a smaller form factor and it gives real-time 3D information. Here, I'm pressing a USB connector into the sensor, and you can see on the right-hand side the real-time output of the camera, and on the left, 3D information, which is useful for pose estimation. This sensor can also pick up fine texture, as you can see on the barrel of the screwdriver. Advancements in robotic tactile sensing will lead to increased automation in applications where human hands are used today. Robotic grippers will become more intelligent and reusable. Robotic systems will be able to complete complex assemblies and handle objects with ease, and robots will be able to live in our homes and navigate and manipulate an unconstrained world. We have more information about our products for high-resolution 3D measurement and robotic tactile sensing on our website, www.gelsight.com. We are excited to collaborate with Facebook on the Digit and to be part of this effort to expand the field of digital tactile sensing.